Hello, my name is Greg Krinkelaw, and I'm the developer of SkyTools. In this video, we are going to set up a basic imaging system. There will be subsequent videos that get into some of the more advanced aspects of that. Now, back in the 1960s, they had a saying, garbage in equals garbage out, and SkyTools is sort of the ultimate example of that. So I urge you to try to get your imaging system set up as completely and thoroughly as possible before you get started trying to use it. How do we set up an imaging system? Well, we can click on Setup, select Imaging Systems. We can find the imaging system, click on the gear icon. Now, if you hunt around on here, you're not going to see a New button. And there's a reason for that. And that is because there are a lot of settings here, and there are a lot of different kinds of imaging systems. So it's hard to come up with a proper set of default values that will work for everyone. So what we've done instead is we've shipped it with a range of imaging systems to choose from. You pick the one that is closest to what you want to create for yourself, and then click the clone button. So for instance, we have a DSLR on an EQ mount. We've got another DSLR connected to a telescope. We have a hyperstar setup. We're going to start with this one here. It's probably the most generic, and we're going to create a telescope that's actually pretty similar. So now that we've selected one, we click the clone button, and we type in TPO 12 inch. The first thing we want to do is set up the system type. This tells the scheduler what kind of access we have to the telescope. If it's a private system, we have complete access to it. If it's shared by night, we have access to it one night at a time. If it's shared by time slot, we have access to it only for a period of time each night. This is a private system. The next thing we want to do is set up the optical tube assembly, the OTA. This is the actual telescope. So I'll click on that. Now it's important that you don't just start editing this, because this OTA is already shared. We want to create a new OTA, and we'll do that with this button here. We could also create a new one by clicking on the OTA pool. These are telescopes that are shipped with SkyTools. We can narrow things down by the make and model, aperture. If we select one of those, it will fill in the basic data. But we're going to click New OTA and type in TPO 12 inch. We're going to choose the type. It's an RC. We're going to click this through to millimeters and enter 305 for the aperture, and the focal length is 2440, which automatically gives us f8. Now, this particular telescope has a built-in focal changer. It's got a reducer, a 0.75 times reducer. So we're going to just go ahead and account for that by putting 0.75 times 8 is f6, which brings the focal length down to 1830. It's got a built-in focal changer, so we'll check this box. That just tells us there's an additional piece of glass. And then the orientation is unmodified. That's going to be the case for most imaging systems. The central obstruction has been estimated based on the type of system, but it turns out for this one it's actually a whopping 48%. So I'm going to put that in. We can ignore all of this, and we're now ready. We can go ahead and click OK. The next thing to set up is the camera. So I'm going to click on the camera. This is an astronomical CCD camera. I can go ahead and type in all these values. Unlike the OTA, this is stored with the imaging system, so I can modify this and it won't affect any of the other imaging systems. We can select Get Camera from Pool. So these are cameras that ship with SkyTools. We can select one of those and it will enter the data for it. We can browse shared cameras. These are cameras that people have shared online. And if we've already set up a camera, it will be in the Your Camera database, and we can select one of those. What we're going to do is we're going to get one from the pool This camera is an SBIG STL6303. That's this one. So I'm going to click use this camera, and now we've filled in all the data. This is the full well. That is how many electrons can be received by a pixel before it saturates. If some cameras have an anti-blooming gate, in which case you fill in this and the saturation level, say 1,000 times. Sometimes a camera is used for photometry, in which case we want to know how far we can go to the full well before it becomes nonlinear. Sometimes that's usually something like 75%. Fill in all these others. The dark signal is 5 electrons per second. The bit depth is 16. And it's already got a gain setting. I'm going to go into a little bit on the gain settings for a basic camera. What the gain does is it takes the number of electrons that have been counted in the well, you divide that by the gain, and it converts it to ADU. So that's the actual signal you're going to get out of the camera. Now, this camera has a gain of 1.5. So I'm just going to type that in there. And there's an additional offset or pedestal of 100 ADU that's added to each of the values. This is to keep things from going negative when you're doing your calibration. I could type in a label here for the gain, but it will make one up based on the numbers. This applies to any binning. Now this is here because some cameras use a different gain depending on the binning. So if this was one of those cameras, I would set up a gain for the 1 times binning, and I would enter that, and then I would come back and set up another gain for the 2 times binning. Or some of them will use one gain for 1 times and another gain for all the other binning, in which case you would select this. But this one will work for any, so I'm going to go ahead and select that. We'll have a special video on setting up the ZWO gains, so that will be later on. I'm going to go ahead and click OK. And we added a gain setting. We added this one here. This was the previous one. I'm going to go ahead and delete that. So here's our gain setting. The next thing is the quantum efficiency of the detector. You can select a camera. In this case, it was the 6303E, and that automatically fills in the numbers. A lot of times you won't have that, so you'll have to select manual entry and put these numbers in here. That can be done from a graph, and we'll have a special video on doing that. If the camera has a built-in offset guider chip, then we'll enable that here, and we'll put in the numbers for that. This is the offset from the center in millimeters. This is the size of the pixels in microns and the number of pixels in the camera. But in this case, we don't have one of those, so I'm going to turn that off. Now, if we wanted to save this camera, we could click here and enter description and click save, and that will save it to a SkyTools.stx file, which can then be read in by another SkyTools user. So that's a way of sharing your camera setup. We could also click share here, and that will upload it to our website, and that's what people browse when they click browse shared cameras. I encourage people to do that because setting up cameras is difficult. You'll have to go find the data if it's not already in here. So sharing it with other people keeps them from having to do the same thing. Once we close this, it'll be added to the Your Cameras database so we can apply it to another imaging system. So I'm going to go ahead and click Done. This is the optical configuration. Primary focus, prime focus, piggyback, camera only, eyepiece projection. Now most people will just leave it at primary focus, and it can be a little confusing here. There's primary focus and prime focus. Primary focus simply means where a camera would normally be placed on this type of telescope. So if it's a refractor, it's at the back end of the telescope. If it's a Newtonian, it's up where the eyepiece focuser is. That is what we're considering the primary focus. Prime focus is where the primary mirror or lens focuses. In some cases, the secondary mirror is removed and something like a hyperstar camera is put in its place. And that would be placing the camera at the prime focus. But this one's going to be in the normal focus. If you have focal reducers and extenders that you swap in and out, then you can add those here. Click the Add button. We put in the magnification factor. Say it's a 0.5 time focal reducer, the barrel diameter, and click OK. And we've added that here. I'm going to go ahead and delete it. In fact, I'm going to delete all of these because this one doesn't have any. There, now we don't have any. The next thing are our efficiencies. Now, if this is a refracting telescope, then these would be grayed out. But for telescopes with mirrors, it turns out that there's a pretty big degradation in the signal you get out of a telescope based on the last time that the mirrors were cleaned. So we're going to put in the date of the last time the mirrors were cleaned, 2020, January 1st. And the secondary mirror was cleaned at the same time, so I'm just going to click Same. And then we're going to click the Advanced button, and that brings up the efficiencies. Now we can set efficiencies per filter. We haven't defined any filters yet, but we could do that. That's a more advanced topic for a future video. As is the mirror degradation coefficient, we'll just leave that at 6,000. But this is a number that's important to be entered. If you've been using this imaging system for a while, you've probably noticed that even on the best night, the stars don't get any sharper than a certain full width of half max. And so we put that number in here. In this particular system, it doesn't seem to get any better than a full width of half max of 1.8, no matter how good the seeing is. And this will let SkyTools know that so it can use that in its calculations. Here we set up the location. Now, if we just select a location, that will be the default location. So when we first open it, this will be the default location. If it's in a fixed location, say in an observatory, then we click the fixed box. And if we do that, we won't be able to select the location. But that's okay because it's always in the same spot. The next thing is the control system. And this is important because this is what tells SkyTools how the system works and what components you have that are automated. So it's very important to get this set up correctly. Starting with the actual control, it could be a hand controller, a computer control of some kind. We could use the SkyTools built-in real-time mount control. We can use ACP. ACP with the eye telescope extensions, that would be for an eye telescope. And ACP Expert, that would be if we're using ACP Scheduler. This one uses SkyTools real-time for control, so we're going to select that. We do have an auto guider, so we're going to select that. There's a focus max for autofocus, so that's turned on, and we have a camera rotator. Now we'll enter our timings. These numbers help the scheduler keep things scheduled with the proper timing, because every time you slew or change a filter, it takes a certain amount of time, and when it's building a schedule, it needs to at least have a general idea of how long that's going to take. Probably the most important is the time between subsequent exposures, and in this case, it's 30 seconds. The next is the slew rate. Now, this isn't what comes from the manufacturer. This is sort of a mean value that you can determine by doing some different slews across the sky. You discover that you went 30 degrees and it took 30 seconds, then that means on the average it's going 1 degree per second. This is difficult to model because a lot of times the mounts will start out slow, then they'll speed up, then they'll slow down again, and so forth. but we only really just need a general idea of how long the slew is going to take. So run some different slews in different parts of the sky and see generally how fast it moves in degrees per second in both RA and DEC. We enter the time for a filter change, and that includes focusing after the change. In this case, we've got full 5 minutes. I guess that's because we're doing it manually. I don't know. Actually, for this telescope, it only takes 12 seconds. This is how long it takes to do a focus from scratch. This is how long it takes to find the field or to update your pointing, again, on average. It doesn't have to be exact. If we're using a gem mount, this would be how long it takes to do a meridian flip. And I think we sort of skipped over the mount here. We'll go back to that in a minute. This is how long it takes the guider to settle, because it can wait before it gets going. This is the camera rotation rate. This one rotates at 12 degrees per second. Flat fields, changing a focal extender, reducer, that sort of thing. We're going to go ahead and click OK. Now we skipped over the mount up here. This one is actually a fork equatorial wedge, but I'm going to put it back to a German equatorial because the next thing we're going to look at are setting up a German equatorial mount. Now what we're doing here is we're determining how far we can go past the meridian in either direction before we have to flip. So starting with the telescope on the east side of the pier, usually looking west, how far can we go past the meridian before we have to flip? And we're doing that in minutes, and that's minutes of time or minutes of hour angle. They're basically the same thing. And in this case, it can go 60 minutes past the meridian. Now with the mount on the west side, we can do the same thing. It's a similar 60 minutes past the meridian before it has to flip. Now we'll set up the camera. This is the position angle of the camera, measured from north to the east. If that's fixed, click this. But remember, we had a rotator, so we're not going to select fixed. So this can change with time. This is the maximum binning allowed for the camera. In this case, it's ×2. If you've got, say, a color camera, that would just always be ×1. But this camera will go up to ×2 binning. And now we're going to enter our filters. So click on Filters. I'm going to just delete the ones that are already here and enter new ones. Now this camera has a Generation 1 LRGB filters, green, luminance, red, plus a 5 nanometer H alpha and a V filter. Now I'm going to click on View Edit to see what these look like. What we've got here is wavelength versus transparency. This filter has its maximum transparency at about 550 nanometers. These are in nanometers. And we'll look at how you enter your own filter data in a separate video. There's 3 types of labels for a filter. This is the full long version of the label. This is the abbreviation when the software doesn't have a lot of room to put the whole label in. And if you're using ACP, this label must match the label that is input into ACP. So that's filters. Click OK. Lenses, if this is a DSLR, we would assign lenses. There'll be a special DSLR video eventually. Exposure times. Here's where we set limits on our exposure times. We can go ahead and set a range, in this case from 30 seconds to 5 minutes. Or we can set a list of allowed exposure times. And you use this in the case where you have pre-set up calibrations at specific exposure times. So in that case, maybe we have calibrations for 60-second exposures, 2-minute exposures, 3-minute exposures, and 5-minute exposures. So it would only allow these specific exposure times. But we're going to go back to here and set it for 30 seconds to 5 minutes and click OK. So SkyTools will only select exposure times within that range. Next, we're going to configure the guider field of view indicators. And there's two kinds of guiders. There's the off-axis guider and the external guide scope. Now, if you don't have a guider, then select none. But we're going to set up an off-axis guider. Now, to do that, we need to know the distance, the separation from the center of the guider field of view to the center of the main camera field of view. And we can specify that in millimeters if we go out and measure it, or we can specify it in arc minutes if we measure it in the sky. In this case, it's 12 arc minutes. The next thing to add is the position angle of the guider relative to the main camera. And it turns out that's at 90 degrees, again measured from north to the east. If we were setting up a guide scope, the only difference is we can enter the focal length of the guide scope here. In some cases, the guider field of view can be rotated with respect to the position angle of the main camera. So it's not oriented in exactly the same way. In that case, we would enter that value here. These are important numbers. This determines the preferred magnitude range for the guide stars. So let's say any star brighter than 8th magnitude saturates and it doesn't like guiding on those bright stars, and anything fainter than 12th magnitude doesn't work reliably. So for this particular auto guider, it likes stars between 8th and 12th magnitude. Here's the basic data for the guide camera: 648 by 486 pixels, 7.4 micron pixels. This will determine the scale. All right, we're all set up, and we'll click OK. We're not going to set up for eyepiece projection. That will be a special video somewhere down the road. I think we're done. We've created our imaging system. Let's go ahead and click on Report, and this will tell us all about the imaging system that we've created. Important to go over this data to see that it makes good sense. These are the two binning levels. If we had different focal reducers and exchangers, it would add those in here. Each one affects the field of view or the image scale. And in this case, it's telling us that at 1 times binning, it's appropriate for astrometry. Okay, now if we wanted to save this entire imaging system, we could click on Save here, type in a description, and it would write it to a skytools.sdx file, which we could then share with another user. They could read it in using the Open button here, read in that SDX file, and that would transfer that imaging system to them. So I'm going to go ahead and click Done and select the imaging system we just created. It's going to recalculate. Notice that the location is grayed out. That's because we said it was a fixed location, so we're not allowed to change it. If we put in multiple focal changers, reducers, extenders, that sort of thing, we'd be able to select them here. In most cases, we could set this to auto or primary focus. It's not going to matter. We can select a specific filter for the calculations down here, or leave that at auto filter. And remember, we set this that it could only do 1 or 2 times binning. We can leave that in auto as well. So that's how we set up an imaging system in SkyTools for imaging.